In this video, we're looking at the solution to a final exam review problem, problem number 1. Okay. In problem number 1, the very first thing that we're asking to do is look at the transfer function for this difference equation. And so if you'll remember, difference equations are the discrete time equivalent of differential equations. And so we've talked about a z-transform, and one of the things that we have with a z-transform is that if you have a signal, let's call it g of n, if you have a signal g of n and it has a z-transform g of z, then if you delay that signal by, say, 1, then the resulting transform is g of z times z to the minus 1. If you delay it by like 6, then the resulting transform is g of z, z to the minus 6. So we look at this difference equation and we take the z transform of both sides, and we will get the following. When we start and we look at y of n, that becomes y of z. Then we have minus 0.8. And we notice we have a delay by 1, so this would be z to the minus 1, y of z. And next we have a delay by 2, so this is 0.15, z to the minus 2, y of z. And now we can move to the x side of the equation. We have x by itself, x of n, no delays, so that's just x of z. And then minus 0.75 z to the minus 1, because x, that particular term is delayed by 1, z to the minus 1 x of z. All right, so that's the z transform of the equation, and now it's just a matter of algebra to get the transfer function, because we factor out y to the z. And we factor out x of z. And then we write h of z, the transfer function, as y of z over x of z. And it's 1 minus 0.75 z to the minus 1 over 1 minus 0.8 z to the minus 1 plus 0.15 z to the minus 2. Okay, so at this point we now have the transfer function for the signal h of z, and it's given by this expression. So what I want you to notice is you could have gone straight to this answer. We talked about that some in class, that this always works out to have the same type of form of a solution. And so we look at the original difference equation and we see, let me clean this up a little bit so I can point to things. Okay, we see the coefficients in front of the y. So there's a 1 in front of y of n, there's a minus 0.8 in front of y of n minus 1, there's a 0.15 in front of y of n minus 2. And on the x side of the equation, we have a 1 in front of x of n and a minus 0.75 in front of x of n minus 1. Well, the x's show up in the numerator and the y's show up in the denominator. And so you notice here's the 1 coefficient for the term in front of y of n. Here's the minus 0.8. Here's the plus 0.15. These show up in the denominator. In the numerator, we have the 1 in front of x of n and the minus 0.75 in front of x of n minus 1. So you can just go straight to the answer, but this is the reason why we arrive at this particular form. Okay, so that's the answer to part A. Part B, we want to know, is this system BIBO? Okay, and so the way we look at that is we look at the denominator of h of z. and we set the characteristic, this is the characteristic equation, we set that equal to 0. Well, that's what a characteristic equation is. It's the denominator set to 0. You get the characteristic equation. And now you solve for z. Okay, so this would just be standard, plug this into your calculator and solve. Okay, so when you do that, you get z is equal to, let me check here. I get z is equal to 0.3 and 0.5. Okay, so those are the two roots of z, and if you plotted those in the z plane, we'd have something here at 0.3, there's a pole, at 0.5 there's a pole, here's the unit circle, move that down a little bit, here's a unit circle. These poles are completely inside the unit circle. All right, so check, yes, this is BIBO. All right, and we'll talk a little bit more about that in a second. All right, so moving on to part C. All right, in part C, I'm asking you to find what the steady state solution would be when x of n is equal to 3. All right, so if you think back, way back to the beginning of the course, we looked at how to find the particular solution for a differential equation, and the same trick works for discrete time systems. You just need to figure out, what the x value is and what the z value would be. So we're starting with a forcing function of the form x z to the n. Okay, I want that to be a constant. Okay, so I think it's fairly obvious that if I put z equal 1 and x equal 3, that will do the job, because when I make those substitutions, I get 3 times 1 to the n, which is, 1 to the n is always 1, so this is 3. So it's the same type of deal. So if I start with the z value and the cap x value, I can find the output, steady state output form as y, because, I'm sorry, let me back up a second. The steady state output value, y of n, is going to be of the form cap y, z to the n, where z is the same thing. Okay, z is what we started with. In this case, we're starting with a 1. All right, and then cap y is cap x times h of z evaluated at the z value. All right, so this should look familiar to you because we did it for Laplace transforms. All right, we actually talked about this in class, but I went really, really fast on it. So that's what I'm trying to do here. All right, so I go back and I look at h of z, and I can copy that down from up here. I know what h of z is, so let me put it here. So there's h, okay, and I just plug in. All right, so I would have h of 1 is equal to 1 minus 0.75 divided by 1 minus 0.8 plus 0.15, and the answer I get for that is, hang on just a second, I got to recalculate that. I get 0.7143. All right, and then cap y is going to be h of z times cap x. So I essentially need to multiply h by 3, and what I get is 2.1429. All right, so that tells you the answer, the steady state output for this difference equation. If you have x is equal to 3, the steady state output value is going to be 2.1429. Okay, so that's the answer for part C. All right. In part D, we are looking at the general form of the solution for the total solution for the case where x is equal to 3. So it's the same type of deal. We're still using a forcing function of x equals 3, but the question is, what does the total solution look like? So remember, the total solution is going to be the homogeneous solution plus the particular solution. Sometimes I use the word steady state solution to mean particular solution, and that's going to be true for all stable systems. Steady state. Okay, so we calculated the steady state solution already, and we know the form of the homogeneous solution is going to be C1, and our two roots were 0.3, so 0.3 to the n, and the other root was 0.5, and then we add in our particular solution. So this is the answer that I was looking for in part D. Okay. All right, now quickly moving to parts E and F. Okay, so scrolling back up here to look at the problem statements. We want to do the same thing for a different forcing function. This time the forcing function is going to be a cosine. All right, so let me highlight that. The forcing function is cosine, and we have a frequency of pi over 4. All right, so what I need to do is go down and look at, this would be part E. All right, we want x of n to be x z to the n, and we want this to look like a cosine function. Okay, so we did a similar thing with Laplace where we let s equal j omega, where omega was the frequency. This time it's going to be a little different because the form for discrete transforms is different than for Laplace transforms. Okay, so here we go, let's move forward. If I let z be e to the j omega, okay, so z is e to the j omega, then I could plug into this original function x of n, and I would see that I get a complex exponential. Okay, so this would be x e to the j omega n. But what I remember is Euler's identity, that e to the j omega n is cosine omega n plus j sine omega n. All right, so this is starting to look like the cosine forcing function. Okay, we did this before with Laplace. We introduced something that had this extra complex term, with the j in front of it, and we solved, and then at the end we just took the real part back and ignored the j part. So, that's the short version of this, is that you can solve for the steady state solution for a cosine or a sine function, forcing function, by letting z equals e to the j omega. All right, where omega is the discrete frequency. All right, so we can talk more about discrete frequencies in another problem from this review, but it's not that hard. X of n is cosine pi over 4n. All right, so this is the frequency. Omega is pi over 4. All right, so to find the steady state value y, it's going to be h of z, evaluate at z equals e to the j pi over 4, times x. All right, and so if we're letting x equal, I'm sorry, I forgot the 2. If x is equal to 2 cosine pi over 4n, then the values that we use are z is equal to e to the j pi over 4, and cap x is equal to 2. All right? So we have h of z. It's just a matter of plugging in. You can plug in on your calculator. You would need to use, some strategy to make that happen, because it would be a tedious calculation to plug in, but yet I'd want you to be able to do it. So one of the things you could do is you could program the transfer function into your calculator and then just evaluate this at e to the j pi over 4. All right, and so when I do that, I went ahead and multiplied by 2, because cap x is equal to 2. I get a complex number, so coming out of here I get 2.3487 plus j 0.1942. All right. You could put your calculator in polar form, and what you would get is 2.3567 at e to the j 0.0825. Okay. Now, the last thing you need to do is calculate or convert this to the time domain. All right, and so we get that by taking the magnitude, and we started with a cosine, we end with a cosine, just like we did with Laplace. Our frequency is still pi over 4n, and our angle is 0.0825. And this is in radians, so we're in good shape. Okay, so that's the steady state solution, and which makes it pretty easy to get to part F. In part F, the total solution is going to be the homogeneous solution, which we already know is this, plus the particular solution, which is 2.3567 cosine pi over 4n plus 0.0825. Okay, so there's part F, and the